Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over an introduction to the ideal gas law. So let's get into this. So what is the ideal gas law? Well, the ideal gas law is simply this equation right here. PV equals nRT, or also referred to as Pivnert. Yes, Pivnert. So I usually say PV equals nRT. Some people say Pivnert. If it helps you remember, then by all means use Pivnert. Okay, so what does PV equals nRT mean? Well, P is for pressure, volume, V is for volume, N is for the number of moles, R is the ideal gas constant. I'll talk a little bit more about that in a moment. And T is temperature in kelvins. Now, all of these can be in different units, but we have the temperature in kelvins. Temperature must be in kelvins when you're dealing with gas laws. But for the ideal gas law, what value you use, these can be in different units, right? However, what units you use are going to be dictated by your ideal gas law constant. Now, the constant can have various values, and that's going to be dependent upon what units are used. And I'll talk a little bit more about that in just a moment. But what exactly is R? Well, R is what is known as a proportionality constant. It's a proportion between of different units, right? So right here, I have an example of the value of the R constant, ideal gas constant here. The R is equal to 0.08206 liter atmospheres per mole Kelvin. So this particular iteration of the ideal gas law constant uses these units here, and because it has those units, then this value is the value that's used. So however, there are other values that might be used, right? So um, you could have 8.413, and then here the units are going to be joules per mole Kelvin, right? So here, because the units are different, let me double check that value. I want to make sure I have that right. 314. I have the 4 and the 3 mixed up. So that should be 4. So 8.413 joule Kelvin per mole. So here, instead of having liter atmospheres, liter multiplied by atmospheres, you have joules here over moles Kelvin. And so you'll notice that because the units are different, the value of the R constant is different. However, it's the same constant, right? Exact same constant. The constant doesn't change because you're using different units. It's just the value of the constant changes. Now, it can be shown that liter times atmospheres actually is the same as joules. I believe I do that in another video, so I won't do it here. Just trust me, or don't trust me, just check out my other video. So different values can be used depending on what units you can use that you are using in your constant. Now here you can see it's proportional. It's a division, right? Proportional liter atmospheres over mole Kelvin. Here it's joules over mole Kelvin. So this is a proportionality constant, and it allows us to use various units and relate them together. So we're taking various units and relating them together in our gas law. And so if we had perfect units, then we wouldn't need this constant, but we don't have perfect units. So there you go. All right, so the specific value of R depends on the units. I just talked about that. And if we were dealing with a real gas, we would actually have a gas-specific R constant for that gas, right? But we're not dealing with real gases. We're actually going to be dealing with ideal gases. And I'll talk about the difference between a real gas and an ideal gas in a little bit later. Okay, so is the ideal gas law perfect? Not quite. So bear with me. I'll talk about that in just a moment. Okay, so is the ideal gas law perfect? The answer is no. So it only works for what are called ideal gases. And an ideal gas is one that it's an imaginary perfect gas. So it's not something that we actually exist. It's imaginary in the fact that we're ignoring certain things. So this perfect gas would have no volume and no attractive forces. So obviously that's not going to be the case for real gases. Gases are made up of particles that have mass and therefore they have volume. And so that's one thing that real gases definitely do have in the real world. And then we're assuming for ideal gases that no attractive forces exist. And that's not true. There are attractive forces between atoms and molecules. We have London dispersion forces, van der Waals forces, we have hydrogen bonding, we have dipole-dipole moments, things like that. But we're ignoring all of that for ideal gases. Now, under normal conditions, the real gases actually behave like ideal gases. Why? Because they're moving so fast, they're so far apart, right? So they're going to be so far apart from each other such that the volume taken up by the gas is going to be so huge in comparison to the little itty bitty volume taken up by the particles themselves that it's pretty much negligible and will not have an effect. Same thing goes for attractive forces. The particles are so far apart, they're moving so fast that the attractive forces aren't really acting on them. And if they collide, they're not going to stick together because they collide so hard because they are moving so fast. So now that's only true under normal conditions. If you have conditions of very high pressure or very low temperature, then that's not gonna hold, right? Because under very high pressure, for one instance, you're packing in particles into a container, into maybe a small space. The more you pack in, the smaller the difference is between the size of the volume of the container and the size of the particles. So the distance between the particles and the space taken up by the particles and the particles themselves kind of don't become negligible anymore. At very low temperatures, the molecules or atoms are moving very slow or much slower than normal, such that the intermolecular forces can actually have an effect on them. Okay, so to account for these sorts of things, if we want our ideal gas law to mean more like a real gas law, then we can use what are called correction values or corrective values to account for these properties of gases, to account for the volume of particles and the attractive forces, the intermolecular attractive forces. And so here is the ideal gas law. But then we can add these parts to the ideal gas law to account for intermolecular forces and the actual volume taken up by particles. So this part here is the correction for particle volume. And this part here is for the correction for IMFs. Now this A here, this represents the what are called van der Waals constant. Now the van der Waals constant A is related to the intermolecular forces of a particular substances. So this is going to be different depending on what gas you're looking at. And then this B here is the correction for the volume of a particular particle. And again, that B value is going to be dependent upon what gas you have. So this would be more of the real gas law. So this is what we would use if we wanted to get a more realistic measure of the gases. But for normal purposes, PV equals nRT is perfectly fine. Okay, so after that, now what we're going to be talking about is density and molar mass. So we can use the ideal gas law to solve for molar mass or density, but it's going to require different forms, which I'm going to get into right now. Okay, welcome back. So the question now is, how can we use the ideal gas law to solve for molar mass and density? Well, there's a couple of forms of the equation that you can use. You can either memorize the equation, or you can just learn how to manipulate or rearrange the equation in order to get the equation you want using algebra. My suggestion always as an educator is to encourage you and my students to uh, just learn how to manipulate the equation in order to get from one form to the other rather than simply memorizing, because sometimes your memory isn't going to work. You're going to be stressed, and so you will forget things. But if you know how to manipulate the equation and go from one to the other using algebra, you know your algebra skills, you can always get from one to the other. And so I'm going to show you how to do that in this section of the video. So here we're going to start with PV equals nRT. A couple of basic things we need to remember. Molar mass. Molar mass is equal to grams over mole, mass over the number of moles, right? So we can represent that using the following symbols. I use this strange italicized M, capital M for molar mass, in order to distinguish it from like the capital M for molarity, which is covered in another video. We don't want to confuse symbols. So here we have molar mass is equal to M for mass in grams over the number of moles N. Now, since molar mass is equal to M over N, we can rearrange this so that N is equal to the mass over the molar mass. So this is the molar mass of whatever substance or gas we're looking at, and this would be the mass of the gas. So the number of moles is mass divided by the molar mass. And so in our equation we have N, so we can substitute M over molar mass, the mass over molar mass. We can substitute this in for N, and now we have PV equals M over molar mass multiplied by RT. Now, at this point, we can rearrange this equation and get molar mass is equal to the mass of the gas multiplied by ideal gas law constant multiplied by the temperature in Kelvin divided by pressure and divided by volume. So here, this would be the equation that you would use to find molar mass. So if you're given the mass of your gas, R, the temperature, the pressure, and the volume, you could use that and plug that in and find the molar mass. So this would be one equation you could memorize. Another thing you want to keep in mind, I have here highlighted, you have M over V. Well, what is M over V? Density, right? So density is the mass over volume, right? And here we have M over V. So all we need to do is substitute D in for density for M over V, because that's what M over V is, it's density. So here we have molar mass is equal to D density multiplied by R multiplied by T in Kelvin divided by P. So here's another equation that you can use for molar mass. So if you're given the density in this case, if you're given density, if you're given R, T, and P, then you can plug those in and get molar mass. A really good mnemonic device, kind of a funny mnemonic device that you can use to remember this one, is that the molar mass kitty always puts dirt over its pee. So there you go. The molar mass kitty always puts dirt over its pee. So those of you who have cats know what I'm talking about. So that's a good mnemonic device, and it's a funny one that you can use to remember that equation. And then all you need to do to get the density, the equation is just rearrange it. Now you have density is equal to the molar mass multiplied by pressure divided by RT. T is temperature. And so here you can memorize this equation. So again, you have a few equations that you could just simply memorize, or if you can remember how to convert from one to the other, just remember that molarity is mass over, not molarity, it's molar mass. So the molar mass is the mass over the number of moles, mass in grams over the number of moles, and then you just manipulate that or rearrange it into N equals M over the molar mass. And then remember, density is equal to mass over volume. So remember these, you can plug those into the equation and manipulate the equation. And that's it. So now I'm going to go over a couple of examples to show you how this is used. Hello everyone, and so I'm going to do a couple of examples to show you how you can use the ideal gas law to solve problems. So example number 1. So here we're asked to determine the volume occupied by 2.34 grams of a particular substance, gas, carbon dioxide, and they give us the pressure and the temperature. Pressure is 1.09 atmospheres and 68 degrees Celsius. So we're going to have to convert a few things into the correct units. So first, we're going to use PV equals nRT. And so remember, the R value, the units are going to depend on which one we use. I always use the 0.08206 liter atmospheres over mole Kelvin. So that's the one I'll be using. So R is equal to that value. And you want to list what you're given in the problem. So the first thing I'm going to write, okay, so I'm given R, or I'm using R. So the R that I'm using is 0.08206, or sometimes it's you might round this to 0.0821. Doesn't matter. So this is going to be atmosphere liters over mole Kelvin. So what this tells us right away, since we're using this version of the ideal gas law constant, that means that anything that we're given has to be in these units. So pressure has to be in atmospheres, volume has to be in liters, moles, the amount of gas that you're given, it has to be in moles, and of course temperature has to be in Kelvin. So let's look at what we're given. So here we're given temperature is 68 degrees Celsius. So we're going to have to add 273.15 to that to get Kelvin. So temperature is given as 68 degrees Celsius. So we're going to add 273.15. And then there we get 341.15 Kelvin. Let me check my math really quick. It's going to be 340, yeah, 341. All right, so here's our Kelvin. So we got our temperature in Kelvin. Great. The next thing we need moles. We're given grams, so we're going to have to convert this to grams. We're going to use the molar mass of carbon dioxide. So we need the formula for carbon dioxide. So you should know how to go from the name to the formula. So carbon dioxide has the formula CO2. So when you calculate the molar mass, that's going to be 44.01. I believe that's what I got calculated. Yep, 0.01 grams per mole. So I can use that as a conversion factor. So I'm going to take the 2.34 grams, so 2.34 grams of CO2 over 1. And I'm going to use this as a conversion factor. So I have grams on the top here. So I'm going to put grams on the bottom. So 44.01 grams of CO2. And on the top, I'm going to have 1 mole of CO2. So now grams cancels out. Grams of CO2, grams of CO2. Now I'm left with moles. And when I calculate that out, I get 0.0532 moles of CO2. So now I have the moles. So N is equal to 0.0532 moles of CO2. And the Pressure, they already give me in atmospheres, which is fine. I don't need to do any conversion for that. So P is equal to 1.09 atmospheres. And what are they asking for? They're asking for determine the volume. So I need to find the volume. So V is a question mark. So I have everything that I need except for V. So now all I need to do is just plug it into the equation and solve. So there's a couple ways you can do this. You could plug it into the equation and then solve, or you could just solve the equation for what you're missing and then plug everything in. So it doesn't really matter how you do it. So if I solve this equation for volume, then volume is going to be equal to nRT over P. And then, so I'm just going to plug everything in. So the number of moles is 0.0532 moles. Actually, let me bring this down a little bit so that we have space. So moles is, so V is equal to 0.0532 moles. R 0.08206, and I'm going to put in the units, liter, atmospheres over mole Kelvin. And then T is temperature. We have temperature 341.15, or you could always round it to 341 or just 341. So 341.15 Kelvin. Okay. And then all of that is going to be over the given pressure. And the pressure that's given us is 1.09 atmospheres, 1.09 atmospheres. Now, it's really important to always write down all your units. I know it seems cumbersome and time-consuming and all of that, but the important thing is that you got to make sure that everything cancels out except for a volume unit. So, moles. Moles on the bottom, moles on top. Moles cancels out. We have atmospheres on top. We have atmospheres on the bottom. Atmospheres cancels out. We have Kelvin on top, Kelvin on the bottom. Kelvin cancels out. The only thing left is L for liters. That's a volume unit, so that is great. So we plug everything into our calculator, and when we calculate it out, we get, let me hold on a second, 1.366 liters. And so that would be the answer. Now, if we're paying attention to significant figures, we have 3 significants here, we have 4, we have 5, we have 3. So technically, we would round this to 1.37 liters, but that's how you get the answer using your ideal gas law. All right, let's move on to example number 2. Actually, I just realized I don't have another example for you. So hopefully that was good enough. Hopefully this helped you out, and now you have a better understanding of the ideal gas law and you know how to use it. I do have another video, or we'll have other videos where I do go over other example problems, so please check those out. If you enjoyed this video, if you learned something from it, then please, by all means, like the video. Hit that like button, share it with your friends. Subscribe to my channel, by the way. Hit that notification bell. And when you hit the notification bell, make sure you hit all, so that way you can receive notifications for all the videos I put out. And also put a comment down in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.